Hi everyone, welcome to part 3 on our video lecture on section 8.8 dealing with numerical integration. In the previous videos, we've seen that there's multiple ways of approximating an integral. Now we can use Riemann sums, or we can also use the trapezoidal rule. Now, as we saw, the trapezoidal rule was generally a lot better than just using Riemann sums, which involved just using rectangles, either focusing on the left endpoint, right endpoint, or the midpoint. Now, in this video, we're going to be talking about a new rule which is going to be better than the other ones. And this rule here is known as Simpson's rule. Now, as opposed to the trapezoidal rule, which approximated the integral by finding areas or trapezoids, the Simpson's rule is going to be approximating an integral by finding the area that's going to be under parabolas. Now, as opposed to the trapezoidal rule in the previous video, I'm not going to go through the derivation for the Simpson's rule. Instead, I'm just going to go straight to the formula in the interest of time. However, if you're interested in the derivation for this formula, I would recommend you to take a look at the book, section 8.8. It goes through a nice derivation. It's a little bit lengthy to go on a video. But without further ado, here is the formula that we're going to be using for Simpson's rule. Simpson's rule tells us that the integral from a to b for f of x dx is approximated by delta x over 3 times f of x naught plus 4 times f of x1 plus 2 times f of x2 plus, and this one here is going to keep an alternating pattern of 4 and 2 going all the way to the second to last term, where you have 4 times f of x of n minus 1 plus f of x of n. Alright, so again, if you're interested in the origin for this alternating pattern of 4 and 2's, I'll defer you to the book. Alright, now, before we proceed, I do want to mention one very important detail. So let's take a look at our graphs here that are comparing the different approaches. So on the first graph, we have the midpoint approximation, which again, it was not too bad. It was better than the left endpoint approximation. Then on the second graph here, we have the trapezoidal approximation, which was even better. But now on this third graph, we have the Simpson's rule approximation. And what I want you to know here is that we are essentially approximating the area underneath the curve using a parabola. And here we have the parabola. So this is the shape. But notice here that with each of these parabolas, we essentially have 3 points to consider. Now, when we're considering these 3 points, I want you to note that the parabola itself is taking into account 2 subintervals, the interval from x0 to x1 and the interval from x1 to x2. So because of this reason, whenever you're using Simpson's rule, your n, your number of subintervals, has to be even. Because again, each parabola is taking into account 2 subintervals. If you notice a problem that it's telling you that, oh, let's go ahead and use 5 subintervals or 7 subintervals and use Simpson's rule, you cannot. Simpson's rule only works with n is even. Okay, so with that out of the way, let's go ahead and take a look at a problem involving Simpson's rule. So for this problem, we want to use Simpson's rule with n equals to 6. Okay, so n is even, we can use it to approximate the integral from 0 to 1 of sine of x squared dx. So it's the same problem that we did before with the trapezoidal rule. Now we want to round our final result to 3 decimal places and compare this result to the value that we're given with the calculator with the function, integration function, or fn_int, which I just realized that I did not use it on the previous problem, but that's okay because we'll use it in this problem. Alrighty, so with this one here, I'm not going to bother with the sketch because it's going to be the same one as before. However, our delta x is going to be a little bit different. Because now, since we have n equals to 6, then our delta x is going to be equals to 1 minus 0 over 6, which is just going to be 1/6. Okay, alrighty. So, for this one here, I'm not going to bother writing the fractions as a decimals because, well, 1/6, it was not as nice as a decimal as 1/5. So I'm just going to keep the fractions here. And if we picture our x-axis, we're going to be dealing with the following subintervals: 0, then 1/6, then 2/6, which we could simplify it here as 1/3, but I'm going to keep it as is. So I'll keep the 1/6 through 6, 3/6, 4/6, 5/6, and 6/6. And the reason that I'm keeping it like this is because, yes, I just want to remind myself that each of my subintervals has a width of delta x being 1/6. Okay, now using the formula, so we know that the area is going to be approximated by delta x, so delta x being 1/6 divided by 3, which again, I'm going to go ahead and rewrite this one here as 1/3 times the delta x, which was 1/6. Okay, so there's our delta x divided by 3 times f of x naught, so our starting point here is going to be f of 0. Now, I'll continue writing it here, guys, plus, and this is where we start our pattern, 4 times the next function evaluation plus 2 times the next function evaluation plus 4, the next function evaluation plus 2 times the next function evaluation plus 4 times the next function evaluation. And lastly, we end here at our right endpoint given by f of, or the height of the right endpoint given by f of 6/6. Which again, I mean, could you have simplified it? Yes, but I wanted to see the pattern there. Okay, so now let's see what would we get into the calculator. So putting all of this into my calculator, I get the following. The area here is approximately 0.3110. Okay, so this is the approximation given by Simpson's rule. Now let's actually use a calculator to get it. So how do we access the fn int function to the calculator? Well, let me open it up here. Okay, so what we do here is we click on second math. Sorry, whoops, not second math. We just click on math and we scroll down all the way to the 9th option where we see here the fn int option. So we click on it. And now, if you have the newer types of calculator, you should see this. This calculator here is giving us the integral, and we just need to fill it out. This particular integral was going from 0 to 1, and the function was the sine of x squared, and we were integrating with respect to the variable x. Okay, so now that we've set up the integral, we click on enter, and lo and behold, guys, we're getting pretty much the same thing, 0.310. So you see here that at just 3 decimal places, the Simpson's rule with only 6 subintervals was pretty much matching the value that the calculator is getting. Now, this is not to say that the calculator is using Simpson's rule, but it is using it's also using a numerical integration. It is using something a little more complicated, but Simpson's rule is very efficient. Okay, now what if you don't have these newer types of calculators? Well, if you don't have these newer types of calculators, there's another way of doing it. You can still use the math int, but if you click on it, the setup is a little bit different, and to be honest, I don't remember how the setup went. However, I'll show you the way that I did it with my old calculator. So what we can do here is go to the graph, and there we go. This is the sine of x squared function. So once you're in the graph here, what you can do is click on second. Well, let me clear this so you guys can see it. You can click on second calc, and then you go to the 7th option, and this one here is the numerical approximation for an integral. So with the lower limit, you can just click on 0, which was our lower limit. The upper limit was 1, and there we go. Now you visually see the area underneath the curve. And notice here, you're still getting the same value, 0.310. Okay. Now, these are all the examples that I'm going to be going over Simpson's rule because, well, with numerical integration, we don't have to bang our head against the wall thinking about which integration technique may work. No, it's just a matter of remembering the formula and plugging and chugging. Now, there is one more topic that I do want to cover in this section, and this next topic here is error analysis. So all the techniques that we've been covering, after all, were approximation techniques, so they will not, usually, result in the exact value for a definite integral. So, the way that you can calculate the absolute error is the following way. The absolute error is the absolute value of the actual value minus the approximation. Now, oftentimes though, it is better to measure the error in a different way. We can measure it with the relative error, which is defined here as the absolute error divided by the absolute value of the actual value, and also as the percentage relative error, which is the absolute error divided by the absolute value of the actual value times 100. But here's the thing though, what if we don't know the exact value of the integral? Because after all, that's why we were using the approximation techniques. Well, in those scenarios, we might not be able to get the absolute error. However, we can still get some useful information, and that useful information is the maximum value or the upper bound of the error. Now, this is a topic that you guys, if you go on to take higher level math courses, especially with numerical analysis, you'll be delving much more into those topics. However, for this class, I'm just going to give you guys the formulas and use them briefly, but we will not be going into much detail as to how we can actually come up with the formulas. So here's the definition for the maximum value or the upper bound error for the approximation techniques. So if we're dealing with a continuous function f, which has a continuous derivative and continuous second derivative on the closed interval from a to b, then the error e in approximating the integral from a to b for f of x dx with the midpoint rule and the trapezoidal rule is the following. So the error for the midpoint is given by the following inequality. So the absolute value of the error of the midpoint is less than or equals to b minus a raised to the cubed divided by 24n squared times the maximum value of the second derivative. And the error for the trapezoid is given here by the inequality. So the absolute value of the error in the trapezoidal rule is less than or equals to b minus a cubed divided by 12n squared times the maximum of the second derivative of the function. And both of these ones here are on the interval from a to b where the a and b could be included. Now, if f has a continuous fourth derivative function, we can actually also get the error for Simpson's rule. Now, the error for Simpson's rule is given by the following inequality. The absolute value of e is equals to b minus a to the fifth all over 180 times n to the fourth. Now, you're going to multiply all of this times the maximum value of the fourth derivative of x. And this one here again is on the closed interval from a to b. Now, these formulas look a little bit scary here, and they could be, but they're not going to be too bad because I'm going to show you a nice way of thinking about how to handle the maximum values for the second derivative and the fourth derivative. So let's jump straight into an example. Alright, so let's see, can we determine the amount of error in approximating the value of the integral from 0 to 1 of e to the 2x if we're going to be using a trapezoidal rule with 4 subdivisions? Now, this particular problem, we could actually get the absolute error, which we will calculate as well just to compare it, but let's see. What would be the error if we're using the trapezoidal rule with 4 subdivisions? Okay, so we know here that the maximum error when using the trapezoidal rule is going to follow the inequality. The absolute value of the error for the trapezoidal rule has to be less than or equals to b minus a cubed all over 12n squared times the maximum value of the second derivative, but it's on the closed interval from a to b. Okay, so as you get to see here, we need to identify, okay, which one's my a, which one's my b. So for this problem, our a is 0, our b is 1, our n is 4, but what about the second derivative, and what's its maximum value? Well, for the second derivative, we have here, well, let's see. Let's go ahead and calculate the derivatives. So the original function was e to the 2x. So the first derivative is 2 times e to the 2x. And the second derivative is 4 times e to the 2x. Okay? Now, here's the thing though. We don't just want the second derivative. We want to figure out, well, what is its maximum value in the interval from 0 to 1. Now, you might be thinking, okay, well, We already took a calculus course, so we know how we can find the maximum values for function. Well, we can either use the first derivative test, or we can figure out the concavity, but I would argue that there is a quicker approach in this scenario. So think about the second derivative function. It's 4 times e to the 2x. Now the way that this graph looks like is, well, just like a normal exponential. It's e to the 4x, well, 4 times e to the 2x. So it's just an exponential here that is kind of steep. But here's the nice thing about this though. Is this function increasing, decreasing? Well, you see here that this function is always increasing. So what this tells us then is that on the closed interval from 0 to 1, since this function is always increasing, well then the maximum value is the value evaluated at its right endpoint, which in this case, it's 1. So the max is the second derivative evaluated at 1, which in this case is just going to be 4 times e to the 2. Okay, well then it looks like we have everything that we need. So we know that the maximum error for the trapezoidal rule is going to be less than or equals to b minus a, so 1 cubed divided by, let's see, 12 times 4 squared times the maximum value of our second derivative, which was 4e squared. And from this, I got approximately 0.154. All right, so then we know that the maximum error for using a trapezoidal rule with 4 subdivisions is going to be less than or equals to a 0.154. Okay, so what does this mean? Well, for this particular problem, because we can actually figure out what is the exact answer, we can actually get the absolute error. All right, so for this one here, in order to save time, I'm just going to show the problem here on Desmos. All right, so here we have the function e raised to the 2x. I have my lower bound was 0, my upper bound was 1. We were using 4 subintervals, and the exact value for the integral is 3.2608, and a couple more decimal places here. Now, the error is given here. Now, notice here the error, it's not including the absolute value. In our notes, it does have the absolute value, but the error here is 0.0662. Now, what we just did in our work, in fact, let me just move it here. Well, we said that even if we did not know what the actual error was, well, we knew that it had to be less than 1.54. Now, we know the absolute error here. The absolute error is 0.06. So yes, the error is less than 0.154. So let me put here the absolute error, which is, again, it's an absolute value. So the absolute value of negative 0.0662 is indeed less than or equals to a 0.154. So that's essentially what we're doing. Even if we don't know the absolute error, with these formulas, we know how big it can get. Okay, alrighty, so now let's take a look at one more problem here involving the error with Simpson's rule using 4 subdivisions. Now, the approach for this problem is very much the same. It's just that the formula is going to be a little bit different. Now, based on the formula here, we know that the absolute error for Simpson's rule is going to be less than or equals to b minus a raised to the 5th divided by 180 times n to the 4th times the maximum value of the 4th derivative. I'll just put here 4th derivative of f on the closed interval from a to b. And so let's see, what are we going to get? Well, we need to keep on taking derivatives since we do want to get the 4th derivative. So for our second derivative was 4e to the 2x, then the 3rd derivative would be 8e to the 2x, and the 4th derivative is 16e to the 2x. Alrighty, now what is the maximum value for the 4th derivative? Well, we're still dealing with an exponential function, which is always increasing. So the max is simply going to be 16 times e to the 1. All right, so putting everything together, we had b minus a, so it's just 1 minus 0. So 1 divided by 180 times n to the 4th, so 180 times 4 to the 4th times 16 e to the 1st. Sorry, not e to the 1st. It was a function evaluated at 1, so it was 2 times 1, so there we go. So 16 times e squared, which is approximately 0.0025. Now, look at how impressive this is. With only 4 sub-intervals, Simpson's rule is going to have an error that's going to be less than 0.0025. It is very, very accurate. So if you were working on a particular problem and you needed to use numerical integration, then yes, Simpson's rule should be your go-to. Now you might be wondering, well, if Simpson's rule is so effective, then why even bother with the other ones? And you're right, at some point, well, Simpson's rule seems to be vastly superior. However, there are certain functions that, as you're doing the function evaluations, Simpson's rule can actually get more convoluted or require more computing power, that at some point it's actually, even though it gives you a very small error, it might require much more computing power, so another approach might be better. Alrighty, so this is going to be it for this video lecture. Hopefully you guys got, some interest in numerical integration. It's actually very useful. And yeah, this is it for today. I'll see you guys in the next video. Have a good one.